So hello everybody, it's a great pleasure to be here. And so I'll try to illustrate many of the things that Miguel told us just before from laboratory data. So is this working? Yep. So just let me start from this equation as usual. So I will focus on this nonlinear term, and when you go to the lab, we have to simplify the system. Otherwise, it becomes almost impossible to do anything. And I will oversimplify all of it. So there won't be any wind, sorry. There won't be wave breaking. There won't be any current. It will be isotropic, as Miguel said, because in the lab, again, it's not so easy to do anisotropic stuff. It will be homogeneous and stationary. But still, there is still something interesting that remains after removing all this. So let me tell you about the experiment. So in my lab, we have a big facility which is called the Cargèse facility, which is a rotating tank, which is 13 meters in diameter. So it's not done for surface waves; it's done for internal waves, actually. But it's the biggest tank I have in the lab, so that's where I did my surface wave experiments. And so the forcing is done with wedge wave makers that are relatively small, 2 of them in the tank, and they force at relatively the lowest frequency you can go in the lab, which is slightly lower than 1 Hertz, which is very fast for many of you actually, but for me is the slowest I can do. And at the end, we have reflective walls here, no beach, so the waves go back and forth so that they can interact for a long time. And at the end, we get a relatively isotropic state that looks like this. And the kind of measurement we do, we have capacitive probes scattered in the tank, and we do a stereoscopic reconstruction in the middle. So that's a view of the experiment. So we have cameras at the top here. And the issue that we have in the lab as well as in the sea is that we have to see the surface, which is one of the tricky parts for this stereoscopic reconstruction. And in my case, there is no wind, so there are no tiny ripples that you can use in the sea. So here what we do is we just put small plastic particles that float at the surface so that we can see the surface from the cameras. And at the end, the camera look at a part of the tank, which is like 2 meters by 2.5 meters, typically in the middle. And because the conditions are a little bit easier than in the ocean, we have a fairly good vertical resolution of the measurement, which is about 0.5 millimeter. So after processing some tens of terabytes of images, we get a movie like this of the water elevation, from which we can compute the slope actually directly from the gradient. So you see that it's strongly fluctuating, nicely filamentary things. And if you compute directly the magnitude, the root mean square of this gradient, we get the steepness, which in my case is about 10%, 0.1, which is small but not so small in that case. So just a few words on the spectral properties of this wave field. So if we took the usual frequency spectrum, here for 2 different steepness, so the one I showed you before is the blue curve, and we did a stronger run. We get, so the forcing is here, we get a relatively decent decay that looks like a power law, and then we go to the capillary range where different things occur. And if you look at the decay, the dashed line is frequency power -6. This one is -5.2. And that's one of the things in the lab is that we never go observe the -4 scaling. Here is a collection of experiments that were done either by Luc Dijke during his PhD in black or in my lab in blue and red. And you see that, so this is the spectral exponent as a function of the slope. And you see that the exponent is strongly smaller than -4, except when you shake like crazy and you have wave breaking and so on. So that's somehow contradictory because this exponent is supposed to be in the limit of weak turbulence. the -4 prediction, but we never observe them, especially when we go to small slopes. Whereas in the sea, you all know that well, we can get exponents that are very close to -4, even for very very small slopes. So what's the problem here? The problem is dissipation that we cannot avoid. And one tricky thing in the lab also is surface contamination. I mean, surface contamination is extremely efficient to dissipate energy, especially in that range of frequency between 1 and 1 Hertz and 10 Hertz, where the surface contamination is extremely efficient to dam the waves. So we took care to filter the water, to skim the water of the tank. I mean, over more than 100 square meters, it's not an easy thing. Yes. No, the particle is not a problem. They at very tiny ripples, of course, they interact with the waves, but at over a centimeter scale, it's not the particle. We checked without particle and with particle. It doesn't change the spectrum. It's really the surface tension itself. I mean, so we could skim the water as best as we could, and the change of exponent is between the blue symbols and the red symbols. If we skim the water for hours, then the exponent increases, but not really to -4 actually. Because if you don't have the wind to clean up the surface, it's more difficult actually. But the particles themselves, they don't change the spectrum in that range of frequencies.
Okay. Just a quick question. Apart from the dissipation, the big difference here is a isotropic spectrum, right? And
it's isotropic.
Field it's anisotropic. Can that be the possible reason that you don't see?
Well, the theoretical prediction is for isotropic spectrum, as Miguel told you.
Sure. What we see now, right? That's the difference, right?
Sure. I mean, in the sea, it's not isotropic at all. Yeah, sure.
That's what I'm saying. In the field, it's always anisotropic, right? And you see omega to the -4, right? So maybe that works the other way around again.
Yeah. So now, with the stereoscopic data, we can do Fourier transform in both k and omega in frequency. So that's how it looks like. So it's integrated over the directions of k. So we just have k modulus here and frequency here. And the color is energy, the energy spectrum, the elevation spectrum actually. And we see that, so the red line is the linear dispersion relation. I will talk about the dashed line later. And so we see that most of the energy is on this line, but we also see that we have lots of things out of this line, which is probably not a surface for, not a surprise for all of you. And if we do a cut at 2.3 Hertz, so here at this frequency, so that we have the directionality of the spectrum, kx here and ky there, we see that the energy is decently isotropic, as you discussed. And we see also that we have all these bound waves out of the linear dispersion relation. And so there are some lines that we can see, some kind of applied psychology to see if there are lines in there, but the dashed lines are a little bit more visible, at least on my laptop, maybe not here. And these are actually the dispersion relation shifted by the peak spectrum of the spectrum around there. So that's some kind of specific bound waves. So the bound waves are just Fourier modes that are coupled, as Miguel told us, by non-resonant triadic interactions. But of course you also have a second harmonic and higher harmonics that are hidden in this kind of blurred region where there are lots of energy as well. So one problem that we have in the lab is that our experiments are small compared to the Pacific Ocean. And when you have waves in a finite box, then you have modes, discrete modes. and that's almost impossible to avoid in a tank, whichever size it is, even if it's 50 meter. And the consequence of that, if you zoom in this region of the spectrum, we have all these lines here that are discrete modes of the tank. And actually, if you choose one of these, these are two examples of modes that we can have for like 0.701 hertz and 0.738 hertz that are Bessel functions. And if you do the average of the velocity squared at this the same at frequencies that correspond to peaks that are very close to this frequency, we recover in the region where we do the measurement, which is the rectangle, the white rectangle here, we recover something that really looks like this. And these modes actually are a pain because the theory is in the limit of infinite size, and the pain with that is that they deplete the number of resonance you can have that transfer energy to initiate the cascade, and to compensate to some extent for these discrete modes, you have to do a strong increase the non-linearity mostly. Okay, so one question, because I never trust too much the theoreticians. I mean, you have to be cautious with these people. Is can we observe these wave-wave interactions in this signal, and to what extent do they resemble the theory? So, of course, I don't have the exact same notations as Miguel. It will be much simpler. So, if we start from the Zakharov equation and we go to the so-called, so my A is B, and my B is something else. so if we go to the so-called interaction representation, where we remove the linear oscillation of the waves, then the evolution for the modulation of the wave looks like this. It's more or less the same, except for this. So we remove this guy and we get the exponential here. And if you want to compute the spectrum at some point, so it's the very first step of the derivation, actually, before the expansion in the power of epsilon that Miguel showed. Then you have to compute this guy, and in there you have a big sum of 4-wave correlations that appear like this. So I will try to see if I can compute this guy from the data to check whether it looks a little bit like Miguel told us before. So just a word about correlators. So if you have, so let me start for two-point correlation. It's easier. So you can compute correlation in space like this. So, and if the field is homogeneous in space, this correlation should depend only on the capital R and not on the small r here. If you go to Fourier space, the consequence of this homogeneity space is that if you do two-wave correlations here, then you have this delta function that appears. So only you will probe only the case where k1 equals k2. And you have the same for three-wave correlation, four-wave correlations of whatever kind you can have here. They all, because of space homogeneity, they are all probing only the resonant k somehow. Okay, so that's a technical thing. The same if you go to frequency space. Actually, I will use correlation in frequency because they are easier to handle and converge than this guy, because this guy is I mean, we have 3 vectors in 2D, so there are 4 parameters, 6 parameters here, whereas in frequency you have only 3 of them, plus the delta correlation that removes one of them, but it's easier to handle. And you could do the thing in both k and omega space, you get the same kind of thing. So here I just wanted to check to say that these estimators, they will only probe resonant wave vectors or frequencies. So actually I will do correlation of the wave elevation, because going to the Miguel's variable b, which after the near identity transformation is the kind of tricky for with experimental data. And my average here is not the average over realization, it's average over space, over the point x where I compute the wave elevation, and over time using a Welch method. So I take a chunk of the a period of the recording. I do the Fourier transform in frequency, and then I average with the next period of whatever duration. I don't remember, like 1 minute or 2 minutes, something like this. And because of this average over space, actually, even though we are working in frequency, we enforce both the frequency resonance and the resonance in K as well. So that's like technical. And actually, I will compute coherences. So like B coherence is the normalized free-wave correlation, so that this B coherence lies in between 0 and 1. So 0 is purely uncorrelated, and 1 is perfectly correlated. And again, because of this delta function here, this object is actually a function of only 2 of these frequencies, because we get the third one from the resonance condition. So for instance, I can pick the omega 2 and omega 3, and I get omega 1 as the sum of the 2. And you can do the same thing for 4-wave correlations. Okay, let me do a little bit of a detour at smaller scale. Actually, we did also some experiment in a small tank like this. So it's getting even further from the sea. Actually, where you shake it like this. Oops. So we shake a small tank, and we do also the space and time resolve measurement with a different technique, so that we get the sea surface resolved in time and space. And in that case, when we shake very smoothly, so the steepness here is 2%, we get a very nice capillary, gravity capillary dispersion relation, again isotropic. And in that case, we have free-wave coupling, so it's easier to understand this thing. So just let me show you how we get the resonance here. So we plot here, it's kx, ky, and frequency. So that's the dispersion relation of the waves. Okay, we pick a vector k1 or k2 here in that case. So the frequency will be given by this point here. So that's the blue vector in these resonance relations. Then we draw again the dispersion relation starting for this point to pick the frequency omega 3 and k3, and the resonance are supposed to be at the interaction of these two surfaces, which is this green line that I show here, and that gives k1. So all the points on of this green line are resonances, and because we have capillary waves and the change of curvature of the dispersion relation, we do have free-wave interactions for this kind of capillary, gravity capillary range. And if I plot them as a function of omega 2 and omega 3, actually we have resonances above this line here. So at high frequency is pure capillary waves, at low frequency is pure gravity waves. Of course, we don't have free-wave correlations here. And we have a separating line here, which is the specific case where the waves are collinear, where we can have also resonances of a collinear wave vector in that case. And if we compute the free-wave, the B coherence, so the free-wave correlations here, then we see that we have indeed correlations. So the color here are logarithmic, so between 10 minus 1 to 10 minus 2.5. We see that we have a lot of correlations actually on this separating line, because the waves, because the wave vector are collinear, then wave packets are propagating in the same direction, so they overlap for a long time actually. So there are very intense correlations here. We have very weak correlation here, but we also have correlations there, where there are no exact resonances here. So the question is why we do see some things here. So we have lines that are discrete modes, but still we have some correlation almost as high here, where there should be no resonances, as here where there are resonances. And the reason for that is what Miguel told us is approximate resonances, because the dispersion relation here is not a singular line, it has a width. So we can allow some detuning in the dispersion relation. You can put the detuning in whichever you want. And if you put a detuning here consistent with the width of the dispersion relation, you get for the 1D resonances, you get a band of approximate resonances that are separated by this dashed line, and that allow actually many approximate resonances in the region where you should not have resonances, exact resonances. Okay, so here what we see in red are approximate resonances that contribute to the free wave correlation. So that's one thing. Then let me go back to the case of gravity waves. So for gravity waves, there are no pure gravity waves. There are no free wave resonances. So the picture to build the resonances involve 4 waves, like this, where you have the resonances are at the intersection of these 2 dispersion relations that you pick on the first one. And so in principle, there should be no free wave resonances, but we can still compute the B-coherence, the free wave correlations, and we get a significant amount of correlation. So here the blue is like 0.1 or kind of in these correlations. So I plot only a part of the map because there are many symmetries in this object. So just to try to simplify a little bit the images, I plot this correlation. So yeah, maybe I was a little bit quick. So here is frequency omega 2, here is frequency omega 3. Frequency omega 1 is the sum of the two, so it lies, you can get it from on this axis, the red axis here. And the value of the colors are the value of the B-coherence. So the reason why we see correlations here is what Miguel told us about bound waves, is that the wave elevation is variable A, while the theory was done on the variable B that you obtain from this near identity change of variables. And here it's what I use is the wave elevation. So you have many bound waves, and this free wave correlation results from bound waves actually. So I can't do the change of variable, but what I can do is to filter out the bound waves in the k omega spectrum around the dispersion relation. And if you recompute the correlations, the free wave correlations only using the free waves, then we get 0. At the accuracy of the measurement, of course, we get a little bit of something here, but here is the forcing frequencies. So at the forcing frequency, the system is not stationary. I mean, we have this wave maker which oscillates, so it's clearly not stationary, and then we have harmonics of the forcing as well. But except from here, at the accuracy of 10⁻², which is more or less the statistical convergence of the data, we get nothing, which is reassuring, actually. Okay, so this B-coherence is a little bit of a headache to understand, but the tree-coherence is even worse. So actually, yeah, it's wrong. Actually, it's tree-coherence. So, okay, so this tree-coherence is a 4-wave correlation, which, because of the resonance relation, is a function of 3 frequencies. Okay, so it's omega 1. The elevation at frequency omega 1 times omega 2 times omega 3 conjugate times omega 4. Here, omega 1 is the omega 3 plus omega 4 minus omega 2. But it's a 3D object, so we have to do cuts to see anything. So the cut I did here, so I pick the frequency omega 2 equal to 3.2 Hertz here. And I get this ugly image here as a function of omega 3 and omega 4. Okay, so let me try to make sense of this image. So here the frequencies can be positive or negative in both directions. And again, omega 1, as I told you, is the omega 3 plus omega 4 minus omega 2. So the 0 is at 3. The 0 of the axis of omega 1 is at 3.2 Hertz here. So now we have many things in this image. So let me just look at this sketch here, which is the different regions in this image. So there are yellow areas here. These yellow areas actually correspond to cases where there are 2 frequencies that have the same sign. Let's say in this one we have all the frequencies are positive, and this corresponds to two interactions that Miguel told about, that we can picture like we have 2 incoming waves, and 2 outgoing waves. Okay, 1, 2, 3, 4. Now, when we go to this part of the correlation, one frequency becomes negative. But because of the symmetries, we have real fields, so there are symmetries in the Fourier transform. Actually, if you permute the frequency omega 1 with frequency omega 4, actually it's the same situation as this one. So it's again 2-2 wave interaction, and the same for here if you shift omega 1 for omega 2. Now there are the white regions here. In these regions, actually, we change the sign of one of the frequency, which actually is equivalent to saying that we have the wave omega 2 here. So it's a 3-1 interaction. So in that region, or this one that you obtain also by shifting some permutation of 2 of the frequencies, we're actually probing a different kind of interaction, which is a 1-to-3 or 3-to-1 interactions. So these ones are supposed to be forbidden from what Miguel told us before. Only the 2-2 interactions are allowed. And the red region is also a 3-to-1 interaction region. Okay, so let me simplify a little bit the image by just taking one of the A. So I will, if I come back, I will take only this part of the image, okay, which is with the dashed line, because the other ones are obtained by symmetry. So it's a little bit complex, I'm sorry, but I don't see any way to, to make it simpler. Okay, so if you remember, this region is supposed to be a 3-to-1. First. So if we look at this image, there are lines that are obvious, that are totally red here, that are cases where 2 of the frequencies are the same, actually. And the correlation on this red line actually is very close to 1, the B-coherence, which means perfect correlation. And that's because actually you can write the correlation in terms of a cumulant development, where all these terms are cases where 2 frequencies are equal. Okay, you change the pairs, and then you have the cumulant, which is all the remaining. So in the development that Miguel told us, actually, the hypothesis of weak turbulence means that these cumulants will be very small, and these guys are supposed to be 1 once you normalize with the B-coherent. So that's what we see here. That we get 1 on these lines that are these specific and boring cases, and weaker, but not so weak. Actually, we see that the correlation is above 0.1 in this here. Little bit weaker there, but not so weak. And in this region, there is this part, which is the 3-to-1 interaction, which should be 0. And it's clearly not 0. I'm missing the scale, but the yellow region here is like 0.1, which is converged. And it's not a matter of statistical convergence and not 0. And again, it's this story of bound waves. If I filter out, if I filter out the bound modes, again, I get a very different picture than this one for the full field. The 3-to-1 resonance vanish, of course, because there are for the free waves, there are no resonances in this part. And most of the coherence actually vanishes, is removed when you go to free waves. And we see that the B-coherence here is very small. It's about 10⁻², and it's barely converged, as a matter of fact, even though we have quite a bit of data. And that's one of the problems is that, so the good news is that it's weak turbulence, because the correlations are very small. I mean, they are supposed to be epsilon 4 or something like this, to be scaling as epsilon 4. So in my case, epsilon is 0.1, so epsilon 4 is 10⁻4. So we are far to converge something at level 10⁻4, even though we have quite a bit of data. And that's the problem of the statistical convergence of small things. I mean, if you want to converge to 1%, you need 10,000 independent realizations of your process, which is more or less what we have here. So we have 20,000 forcing periods, which is quite a bit of data in terms of images. But if I want to converge at 10 minus 3, then I need 100 more data, which means 100 more data is 5 petabytes of images, which becomes to be kind of insane. It's technically, it's feasible, but then processing all these things is just insane. I mean, and so I showed you that for a specific choice of the frequency omega 2, but if we look at this free-wave correlation for different frequencies, we get a similar kind of picture. We remove all these 3-to-1 interactions all the time, and we get very weak correlations in the region where there are resonances of the free waves. Actually, it's 0 here because there are no resonances possible. So this limit is coming from the limit of resonances of the 2-to resonances of the free waves. And to finish, because I think my time must be over. Yes. We tried to do the same thing with Fabrice's data from Leclerc et al. 2015. So when you compute the tree coherence, we get an image that looks very similar to what we get in the lab. We get this cross that correspond to the trivial case, and then we get also these kind of lines that come from the bound waves that are due to these specific lines are due to the peak of the spectrum. Actually, in that case, the peak of the spectrum was 0.35 Hertz, and this shift is the same the bound waves I showed you before in my experiment with the dashed line, and that you can see inside the dispersion relation here. Actually, so most of it is are second harmonics, but some of them are also due to the coupling with the peak of the spectrum here. And we did not at that time we did this calculation. We did not try to filter out the bound waves, but I suspect that we won't see anything at all here because the stiffness in this data was extremely small, like 2%. Which is 5 times smaller than what I have in the lab, and even in the lab with more data than this, we could not converge the correlation. So I suspect that if we remove the bound waves here, we don't see anything at all. Okay. Okay. So to conclude, well, first it's difficult to estimate these coherences. Need huge data sets, and actually what we see is mostly bound waves that have a big impact, especially when the steepness is not very small. And as Miguel said, you should do this near identity, which is transformation, which is described also in this paper, which I don't know if it's feasible for actual data, but at least we can sometimes we can filter them and see that what remains once we remove the bound waves is indeed consistent with what Miguel told us. So we have this 2-to wave coupling, and even though in my case the steepness was quite large, so I mean 0.1 is a relatively large steepness, we still have very weak correlations, which mean that all the hypotheses that are in the theory are actually well verified, at least at this at the stage I showed you for this data. So thank you for your attention.